Well, good afternoon, everybody, and welcome to a very special Facebook Live. My name is Simon Steele. I'm the Senior Director of Education and STEM Programs at the SETI Institute, and I am located in the Southern Bay Area of California, and I'm going to be talking to our fearless team up at the Allen Telescope Array, which is the SETI Institute's own radio telescope facility. And joining me today are Janusz Kulpa, Wael Farah, and Alex Pollak. So welcome, gentlemen. It's very good to speak to you. So let me first of all ask you, where exactly are you in California?
So we're pretty much in Northern California, in the middle of nowhere, very well isolated. It's a bit difficult to, if you're not local, I guess you have no idea. So I would quickly just share one of the Google Maps to roughly show you where we are. So I guess we have members from around the world. So as a landmark, we have San Francisco here. And then if you just drive up around 5 hours with a car in the direction of Redding, so you have the Lassen National Park. And then in the middle of nowhere, I'm kind of quite good at zooming in. I've definitely done that a couple of times. There we go. So there you can see it's kind of called the Head Creek Radio Observatory. And the Head Creek Radio Observatory is the home of the ATA. So in the past, there were other instruments, and now it's kind of mainly used for the ATA. And if you zoom in, you can see all of those dots, and those are the antennas. And me and Wael, we are kind of located at the moment in that building here, with the green shed or the green roof. And that one is the central signal processing building, which also has the observer room. And we are kind of, at the moment, quite fortunate. We live on site. So it's a bit further. It's about a mile away. There's some accommodations. I think if I look right, Janusz should live at the moment here. So that's the location where Janusz is, and Wael lives, and I live kind of in the house here. So that is quite nice. We're very remote and close to the instrument.
Okay. So we're the whole planet at the moment is in a level of isolation, but you are voluntarily in isolation up there in Northern California. Wow.
Yeah.
And so why would you build a radio telescope facility there? You know, surely it'd be easier if you built it in San Francisco to get to.
Yeah, I guess, yeah. Does anyone of you want to answer, or?
Well, I believe there was a study by, if I recall correctly, UC Berkeley, around the Northern California to estimate where is the most quiet region. And by quiet, I mean radio frequency quiet region. That they could build a first telescope, which was, I believe, 64 feet or 65 feet telescope here on site. And they came up with the survey that pointed to Head Creek as the best place to position the telescope because it's very remote. So there's no much human-made obstacles and human-made transmission around. So all the TV, mobile phone, Wi-Fi transmission are creating artifacts or obstacles for radio astronomy. So that's why we are now at that remote location.
Okay, so keeping away from the human-made signals.
Yep.
Good. Well, as you listen in, and we're going to have a tour of the facility in a moment. Please do send in your questions. Any questions you have about the ATA, things that you see that you'd like to know more about. Any questions about radio astronomy in general. We'd be happy to take those questions. And also let us know where you're watching from as well around the world. So I suppose, first of all, you mentioned that you can't have any sort of human-made radio signal. So you can't even use Wi-Fi. Your mobile phones, cell phones are not functioning there.
Exactly. So there is something which we discovered, which is very nice. It's an Ethernet to Lightning adapter for iPhones. So you can use your phone with that cable. And that is kind of the best equipment, the best tool which we have on site personally.
Right. And is it true that you can actually detect when a mobile phone comes close by?
mobile phones, just as a fun fact, if you take this mobile phone, place it on the moon, and point our telescope, the Allen Telescope Array, to the moon, we can actually pick it up as being one of the brightest signals in our sky. And that's only a small mobile phone. So this is just to give you an idea of how much polluted our radio sky is.
And also there's the sensitivity of these telescopes, and we'll probably talk more about that in a little while. So would you like to give us a little tour of the Allen Telescope Array?
I would switch over kind of to the phone. Let me kind of look the audio, 1 second.
And we will say for our viewers, this is an experimental tour as far as the technology is concerned. So bear with us if the signal isn't too good.
Okay, can you hear me?
It's good.
Okay, awesome. So I guess we start outside. So today it's kind of nice and sunny. And what we see here are kind of our telescopes. So at the moment, because we have the broadcast here and we're working around, we're not observing right now, but they're pointed in a direction where it kind of looks very good, similar to your background picture, just to show. But about half an hour before we started, we've done an observation where we kind of checked the instrument to see if all of the antennas, if all of the instruments, if everything works. So that was done about half an hour ago. So you can imagine those dishes are similar to the TV, the satellite dishes which you have at home, but far more sensitive. And in the center of it, what you can't really see behind that second kind of ring in the shroud is the feed, which then detects all of the signals. And all of those antennas are connected to the central signal processing room, where we receive and then kind of process all of the data.
How big are those dishes? It's difficult to get a scale.
So there's kind of, yeah.
Oh, good. We got
I guess we get a perfect human. Yeah. So they're 6.1 meter in diameter.
Okay.
I think kind of Wael didn't, Wael is finishing his thesis now. He's not doing much sports, so he's kind of very excited.
Well, that was a good sprint. We'll see if he can run as fast back.
Yeah.
Yeah. So how many dishes are there in operation there?
So we have 42 dishes. And out of those 42 dishes, we are at the moment kind of using a subset of 10 antennas to commission a new digital signal processing backend, which I'll show you in a bit. Okay. But we are kind of have an ongoing refurbishment program and development program where we upgrading a first generation of those feeds or the receiving part in those antennas to a new generation. So we can have a look at the feeds if you're interested.
Yeah, absolutely. Wael comes back. He's walking now rather than running, I noticed. I was going to say that we got people viewing here from the UK, from Washington, D.C., Germany, Guatemala, Las Vegas, Altoona, Pennsylvania, New Zealand, Southern Maryland, Mexico City, Puerto Rico, Belgium, the Scottish Highlands, probably another good place to put a radio telescope, Kansas City, Lightning Ridge, New South Wales, Portland, Oregon, Chile, Minnesota, Italy, Massachusetts, Australia, North Wales, Oahu, and Monterey, California. So that's a big set of places. And welcome all of you.
That is exciting. Okay, so we have a look at the feed. Hopefully our cable is long enough. Let me kind of quickly stop in the observer room, which we have here, just to show you. We have a lot of kind of feed sensitive data where we have live plots where we see what's going on with the antennas. And then also some screens. So we talked about radio frequency interference. So we have an antenna on our roof which monitors the local environment, and we can see all of those black lines here is a detection of RFI. So even if we are kind of very well shielded, we still receive a lot of kind of RFI, which we have to distinguish between a real signal in the sky.
Right.
Okay.
As you say, there's so much human-made stuff going on.
Okay. I'm not sure if the cable is long enough, but we give it a try. That looks nearly long enough. So that is our kind of central electronics workshop. And that, for example, is one of those feeds. So if we have one which we can slightly open up. So in the antenna, I'm sure which way around. Okay. We have those. As you can see, we have not prepared it. That it was a bit hot that we thought we could show this as well.
It looks like a rocket ship.
It's kind of, it's a death, like a death ray laser. So,
Okay.
and
What are we looking at here?
So the interesting part here is we have that glass cylinder, and in that glass cylinder, what you see here, that copper, the shiny copper bit, that is what actually detects the signal from the sky. And because we want to be very sensitive and be able to detect very faint signal, so it needs to be cooled down. So the entire thing, the glass vessel, is in an ultra high vacuum, and then whatever the complete copper part is cooled down to around 80 Kelvin, 80, 70 Kelvin, which is roughly kind of minus 200 degrees Celsius. I'm not sure what's that in Fahrenheit.
It's cold.
Yeah, cold. Yeah, very cold. So that is basically the heart of the antenna, which we have. And so those antennas which we see here, those are new versions of the antennas which will be deployed on additional antennas, and they're here to be tested. And so if you look over there, if you can see that. So one of those test benches is kind of the antenna here, where we have it connected to a laptop, we cycle it through, and we see that basically everything works. And if that...
Oh, I think we've frozen.
We lost them.
Janusz, would you like to say a few comments on this?
So
while they get back on the.
Currently, we are working on refurbishing the antenna and reprogramming some software on the antennas to make it more robust physically as well. And we have also plans to put new feeds into all 42 antennas, hopefully. But for now, we are aiming at making those 10 antennas that Alex mentioned up and running. So I think they are back. So,
okay.
Hey guys, Janusz, finish your thoughts, definitely.
So you've seen the laptop and one of the feeds, and I'm currently working on that feed. I could remote there to that laptop to pull all the information about the cooling status, about the vacuum pump status, about various sensors inside that enclosure. Because of course we are not only looking at the sky, we have to monitor what state the antennas are at as well, to make sure that the antennas are in perfect working conditions.
Right. Thank you. And Alex and Wael, we got a very good tour before everything froze, so I don't think we lost anything, which is wonderful.
Okay. Perfect. Then I guess let's quickly go through the signal processing room. And tell you where all of the signals from the antennas which we have, which are connected, are ending up, and what is happening then up to the computer where we do the analysis. And then I guess we can have the question. So it is a bit loud in here, so I try to kind of speak much louder because we have a big air conditioning unit. So what you see in front of you, that is where all of the antenna signals come into our central signal processing building. So all of those yellow fiber, those are optical fibers. Each of that pair is connected to one of the 42 antennas. And then after that one, we frequency convert it, and then it's connected to a digitizer. So it's basically the same thing as if you have your microphone, and if you want to record something, you have to digitize it to have it in the computer or in a digital format. And that is what the next step is. For that, let's go around. So after we have the signals being converted. At that time analog, so from the front where you saw the yellow cables, they come out here on those black cables, and then they're connected to, obviously connected, they're then connected to the digital signal processing hardware. And this is what is happening here. So that hardware is kind of, you can compare that like, there's a card in there similar to a motherboard in a computer, which is just designed to digitize a lot of data very fast and very accurate. And that is what is happening here. So we have all of the inputs. So those are the different antennas which come in. In that back end, it's 10 different antennas which are connected. And then we have on this side, the 10 gigabit fiber connectors. So comparable in your home computing or on your home network, the maximum speed which you have is 1 gigabit, for example. Your internet is maybe 100 megabit. And here you have 20 gigabit of data coming out for each of those antennas. And then the signal, when they're digitized, go into those computers here. And they have very expensive graphics cards in it and 40 gigabit Ethernet ports. And they're doing then the analysis and the location. So let me kind of move out of here, and then Wael can take over.
So quick comment, why 2 cables per antennas? We have 2 polarization, X and Y. So we are looking in X and Y polarization on every antenna. So we are not missing the signals that are linearly polarized. I'm not sure how much should I explain what polarization of the signal is.
Maybe just a little bit. That would be, because that's interesting. Yeah.
So basically, I'm not sure if I will correct good enough, but the signal, like the radio frequency signal, the wave could have various modes of polarization, which is. Alex, do you have better explanation for regular viewer?
Yeah, and very easy way is kind of not a good explanation, but where you kind of experience in your own life polarization is if you go to a 3D cinema. So to create the 3D effect, you polarize the image, and then you have those glasses, and for example, one glass is only polarized vertically and the other one only horizontally. So only, those kind of polarized light can come in. So next time if you're at a cinema and you have 2 of those glasses, put them on top of each other and move them, and at one point they will go dark if they're linearly polarized.
Or even better, even better, the old calculators with LCD display were using the polarization to show if the bar is on or off. So if you look at the with polarization glasses at that, you will see that sometimes you see more or less. So any electromagnetic wave has its own way of rotation. So it could be have circular polarization or linear or random. And to be able to pick anything, we need to have 2 orthogonal feeds in the antenna. So either 1 or 2 feeds will be will pick up the photons that are coming to them.
So you'll pick the vertical oscillations and the horizontal oscillations, or some component in between. So as you say, you won't miss anything coming in. Yeah.
Yes.
Yeah. Good. That's good. Thank you. Well, we've got a lot more people viewing. This is really a list of the countries and places around the world. Louisiana, Zurich, France, Maine, Tokyo, Israel, Tennessee, Houston, Texas, Wisconsin, Canada, Liverpool. There's going to be a quiz for you guys afterwards with all these names. Edinburgh, Turkey, Milan, Romania, and Georgia in the US. We've got a couple of questions as well. So are you guys ready for the first questions?
Sure.
The first one actually is, what is the latest unidentified signal you've picked up? This is from Chris. So once you've been monitoring, is there anything that has seemed a little bit peculiar? And are you allowed to tell us?
So There are kind of a lot of signals in the longer history which have been picked up, which kind of people put in as candidates for kind of techno signatures, but none of them has kind of proven to be it. And so recently, so on our side, we're kind of, because we're running those many upgrades, we haven't done SETI observations for a while. So we are very close to, within the next 4 to 6 weeks, we start doing SETI observation with the array here as well. But because we're doing so much maintenance at the moment, and you see all of those feed in the eShop, we haven't picked anything up. But if we pick anything up, it will be.
We picked something recently. I think Wael picked it up, but it was clearly human-made. We were just unable to identify where it came from. So we are picking a lot of human-made signals still.
Yeah, and that's what you have to filter out before you can even go any further than that. There's a lot of noise from human satellites, human on the ground, and everything. So yeah. There's a question from Tyrone. Would it be feasible to use the dish at Arecibo? So there's a question about using Arecibo as a technosignature telescope, which of course it is and has been. How would you compare Arecibo to the ATA? There's certainly some design differences, aren't there?
Yeah, I can take that. So in radio astronomy, there's 2 ways to do radio astronomy. You can either build a really large dish, or so that's called a single dish, or you can go and do interferometry, where you build smaller dishes, and you connect them to each other coherently, and you sum up the signal. So the Arecibo is a single dish instrument. It's massive. Its collecting area is large, but it is limited in the sense that it cannot track properly the sky, because we cannot move largely a single dish really effectively. The difference between it and the ATA is that the ATA is a mechanically much simpler system, in the sense that we can always track the sky, and we can always we have a better handle mechanically of the telescope, and at the same time we have a larger bandwidth, so we can observe the sky at a larger or much higher frequencies.
Okay.
So it really depends. So one of the things there as well, if you have one single dish, you have a very small field of view. So if you have small, it's basically the inverse. The smaller your antenna, as bigger the field of view. And so the ATA was specifically built to look for technosignatures. That's the reason why those antennas are relatively small, with 6 meters compared to other antennas. So you have a big field of view, so you can cover a lot of sky. And then if there's something interesting, what Wael said, if you combine those antennas together, you get a resolution from the distance between the furthest antenna. So the distance between the antennas gives you then the resolution. So you're very flexible with such an instrument.
So to compare that, sometimes you want to use the times 12 scope, but sometimes binoculars are just enough and you are able to sweep much larger terrain with.
Cool. Okay. Thank you. There's a technical question. So I'll ask this as it's written, so maybe you can also translate it for the non-radio astronomers. And this is from David. Are the signals blocked down converted at the dish to avoid cable losses, or are they digitized at the dish?
Awesome. I love those questions. Those are for me the easy questions to answer. There's usually all those, one difficult one. So we actually kind of bring the entire band, so 1 to 12 gigahertz, as an RF into the signal processing room. So the only thing in the feed is we have the low noise amplifier, we detect it, and then we have room temperature amplifiers, so we just amplify the signal a lot, and then we have an coax to optical fiber converter, and then you have it in the fiber, and that is what ends up in the signal processing room. And then in the signal processing room, what you've seen there, we have 4 different tunings where we can select subbands, and those subbands are then shifted in frequency to a lower frequency where they then finally digitized. I hope that that was very detailed. I hope people will follow.
Well, certainly, if people want more answers, we can try and get those for them. But thank you. As a question, does SETI still have a radar site in the Cove near Woodbury, Georgia? I'm not sure. That's before my time.
I guess we started similarly. I'm not sure.
Okay, so that you mean the secret site near Woodbury, Georgia? Yes, we can't answer that question. We've got a few more people watching in from Amarillo, Texas, Belgrade, Huntsville, Alabama, Naples, and North Elm in Norfolk in England, and from Morrisville in Texas. So let's see, there's another question here, and this is from Glenn. With your current program, how close would an Earth need to be for you to be able to identify a signal? So imagine you're on another Earth and you've probably got something maybe the size of the Arecibo transmitter. How far away would you be able to detect that Earth with
I think was it two? I think if I remember right, but maybe quote me or correct me. I think it's around 200,000 light years with kind of the instruments which we have at the moment. So not exclusively the ATA, but for example with Green Bank or Arecibo or kind of Meerkat or that class of radio telescopes, which is roughly, is it a third across the Milky Way, which we can detect that. So we can detect signals up to that.
Okay, so the Milky Way, our galaxy is 100,000 light years across, so we can get about a third of the way, maybe roughly, to detect that, which takes in a lot of stars and a lot of planetary systems, doesn't it? Okay, let's see. Here's a question from Vishnu. Could signals from a different species be completely different from our technology? And therefore, could we be missing them completely? So are we missing something we don't know anything about? So there's the question.
Well, the RF, so the radio frequency signals that we are using started like 140 years ago, 130 years ago. And by design or physics, other techno or civilization that are using radio frequency would be using it, I believe, very similarly to how we are using. Of course, the question is, with our civilization using it only for last 100 years, is it the ultimate communication method, or is there something like, look at the paper mails. We are not longer using paper mails as often as we use emails. So is the RF transmission something that will stay, or it will become obsolete in, say, 100 or 200 years? We don't know that.
So it's a good point to do, yeah. So we don't know, there could be other technologies out there, but the thought process, what we do is, what would another civilization look for, and if they want to detect us? So how are we allowed, or how are we kind of, what do we leak that another civilization could detect us? And that is the thought process. And so we're looking for those signals. But what Janusz said as well, so there is in the Drake equation a term which basically tells you how long a civilization is detectable. And moving on from technology, we already got far more radio quiet than we were in the past. So we are going over, a lot of internet now is over optic cables. There's maybe now with SpaceX, there might be a few more satellites up there, but the trend goes to less power and less power transmission. So
even if we look at the radio used to be a super broadband, super loud, and antennas pointed all over the place. Now, for example, with digital radio or digital TV, the antenna pattern, so the way that antenna is pointed, are mostly around the areas with higher population. So we are not pushing that much signal into the air or into the space in that regard. So this is a huge question, and I don't know if we have any answer to that.
But something exciting to plan for and work out in the future. So
sorry. I haven't been involved in that, but SETI is also doing some laser and optical search. So this is another layer. So we are not only, so our observatory is RF only, but the SETI as a whole is trying to go beyond RF communication only.
Right, and if you wanted to find out more about the laser SETI program, do go to the SETI Institute website, and maybe we'll have a Facebook Live about the optical SETI program soon. That will be great. We've come to the end of our time, and maybe a good last question from Roy before we wrap up. What's it like living and working at Hat Creek? How is it there? It's positives and negatives.
Do you want to start, and then we go around?
Okay, I will show you how the outside world looks from here. So this is, I'm located in the library in the dormitory, and this is the outside world. So there's a lot of animals, lot of birds, deer, squirrels that you could look. But for person who grew up in the major city in Europe, it is very remote. So you need to change your hobbies, the way you're spending time. I'm reading much more books here, for example. I did adapt, but I know that it's not like, not every person, I believe, is able to move to such location and work for a year or so.
Yeah. Which city are you from?
So I was born in Białystok in Poland, but I spent over 12 years in Warsaw, which is like 3 million people city, Poland capital.
Yeah. Okay. So
the closest town here is like 3,000 or so.
Yeah.
So it's a huge difference.
Yeah. And Alex, what about, how does this compare to Oxford?
Remote. I think kind of it has a bit of a double-sided sword. It's like, if you enjoy nature, if you enjoy hiking, it's beautiful. It's a very nice place, and I try to go for runs and everything, but it gets definitely lonely because there's not much social interaction. So the closest bigger city is around 1.5 hours drive away, which is Reading. So, and especially now, before the whole kind of COVID situation, I used to kind of go to Reading on the weekend, but now there's nothing. And it's like, it's definitely can be a bit, isolated, but it's very beautiful.
Yeah. And Wael, how does this compare to back home, or anywhere else you've lived?
I spent the last 4 years in Melbourne, so it's a bit different compared to Melbourne, to say the least. But on a positive note, I think Hat Creek is a good place to be in quarantine. So if you want to pick a place to be self-quarantined, you can come to Hat Creek. If you have a thesis to write, you can come to Hat Creek, because there's literally nothing that can distract you from doing work. So yeah, it's a bittersweet situation, but.
Cool. Well, on that comment, thank you very much, the three of you, for talking this afternoon and giving us a tour of the facilities. And hopefully we'll do another Facebook Live from Hat Creek in the future, and maybe I can get up there as well. That will be fun to have a fun tour. All right, take care, guys. See you soon.
Thank you.